Okay, so we're going to get into orbit section 13.4, and we want to, we're going to learn a little bit about satellites and orbitals around not just the Earth, but all kinds of stuff. So let's talk about satellites. Planets or satellites, stars go around in the center of the galaxy, all kinds of things. So you have to be kind of liberal with your view of what you're thinking about. Nicholas Copernicus, we talked about him and his Copernican tables. He assumed that all of the orbits that he was dealing with were circular orbits. They had, it's not a bad assumption. It's one of the reasons Tycho Brahe had his issue with the predictions. We're going to do that same thing. We're going to assume that all our orbits are circular. And of course, all orbits are elliptical, right? To some degree or another. They have their elliptical eccentricity, they call it. Because there's no such thing as a perfectly circular orbit, all right? But as a first approximation, using a circle works really well. And here's why. Here's what we're avoiding, okay? So if you look at this guy right here, so here's an orbital around a large mass M. Here's a little m. And it's going to go in this loop that's going to just keep going. So it starts here and it goes around the circle and eventually ends up back. I kind of tried to make sure that we ended back up at number 1, but it's not. It's not going to end up back at 1. It'll be a little bit off and it will never get back to that point for a long, long time. In a typical orbit. So what do we call that? We call that apocidal precession. So this is the precession that happens, even though we have each of those loops is actually technically one period. And so that gives us an apocidal period. So instead of going from a period, we'll call it T1 to 2, we have a total apocidal period of T1 all the way through 8 and then back to 1 again. So that's the apocidal period. That is even longer. So all of these things confuse the issue, right? And we don't want to do that. We want to keep it simple. So to avoid this, we're just going to say that R equals a constant. And that's nice, right? It makes it easy for us. And so R is equal to a constant. Here's our radius right here, right, of some mass. This is the mass, the large mass. This is our little orbital mass. And it's got an omega that goes around with. We've got the force of gravity pulling in. Keeping it in its orbit. We're keeping it in its centripetal orbit. Okay, so let's do a little free body diagram thing here where we're going to sum up the forces. The only one really is gravity pulling it in. We know that that's the mass of the orbital times the gravitational field. And here's our mass of the orbital. Here's our field. Okay. We know that that equals our MAC, right? And we're saying, of course, the in is down. Okay, down is positive for this equation. Oh, gosh. I didn't get my nap today. Excuse me. All right, so the MAC, of course, is our V orbital squared divided by the radius. All right. So we're going to take that and we're going to look to find out what is V orbital. So we're using this part and this part. We're putting them together in this equation, and when you solve that equation, canceling out all the different things, you get our v orbital of this. So what is our angular velocity for the orbit? So our angular velocity is v orb equals r times, I'm looking at this equation right here, r times r omega. Omega then is v orb over r. And then we can just substitute that in. This guy can be squared and stuck on the inside of the radical. And that's what it looks like. So what is our period of rotation? What is that period of rotation? Well, we're equating right here omega with 2 pi over our period of rotation. So when you do that, you can solve t equals 2 pi times 1 over the omega. And so 1 over omega is r cubed on top. The mass of the gravitational well is on the bottom, and your universal gravitational constant is on the denominator as well. Take the square root of that, and you've got your period, okay? So let's do an example. What is the speed and period of rotation for a geosynchronous orbital satellite? We showed in class that hopefully you guys were not sleeping when we saw that the geosynchronous radius of orbiting is 4.22 times 10 to the 7 meters. So, great. We want the speed. Okay, so our speed would be v orbital. And we showed earlier that, of course, that is the mass. And we're going to be using Earth, right? The mass of the Earth, because we're talking about a geosynchronous, geo meaning Earth. All right, okay. So I think we're on the same page here. We've got our R geosynchronous, so GS. Plug in a few numbers, 5.96 times 10 to the 24, and we're going to divide that by 4.22 times 10 to the 7. And then all of that times 6.67 times 10 to the minus 11. And over the whole thing, we're going to take the square root. I'm not going to worry about, I know my algebra is good, so I'm just going to slap a meters per second on there because that's what our units should be in the end. But definitely check your units if you're not getting good answers, right? Make sure that you've got your algebra right. So that is 3,070 meters per second. Okay, so that's the speed, right? That's pretty fast. That's quite fast. Oh. Okay. Okay, so that's good. The next question is, what is the period of rotation? Okay, we want to know the period of rotation. We figured out that period of rotation right here. What is tau? Or okay, tau is the common capital T. I don't like using capital T, but we're not doing a whole bunch with tensions anymore, so we're going to call it capital T, and we want to know what that is. How long does that take? If any of you guys are really paying attention, you'll notice that it's geosynchronous, right? So if it's geosynchronous, what does t have to be? All right, pause, think about it for a second if you want. I'm going to give you the answer. It has to be 1 day, right? Because it's going around as the Earth spins. We talked about this in class also. The Earth spins. That satellite above this point has to be the same, right? They don't change their position. This is the same position. So the orbit, the satellite, and you are relative to each other all the time. So if you go around the Earth once in a day, the satellite has to go around the Earth once in a day. So that is 1 day. But of course, we're going to have to check and make sure. Let's verify it. Don't take my word for it. Do a little calculation. So 2 pi, and then we're going to do our r cubed over our mg. And we've got r cubed. Should we just keep it at 2 pi, or should I put in 6.283? And 4.22 times 10 to the 7, and we're going to cube that. We're going to divide by 5.96 times 10 to the 24, and we're going to multiply that by 6.67 times 10 to the minus 11, and then all that has to get the square root business. And lo and behold, you get 86,346 seconds. That is 1 day. So you can verify that that equals 1 day, and you'll be happy to find that it does. There's another way to do it, and that is using the old t equals 2 pi over omega trick, and omega equals v over r, so we've got v over 2 pi r, and this makes sense because this is just x equals vt, right? And we're solving for the time, so time equals our distance over v, and our distance is 2 pi r because it's the circumference. Okay, so all we did here was use x equals vt and the fact that a circumference of a circle is 2 pi r. All right, that is a quicker way to get the answer. We did it the hard way here, but you could certainly, once you have your v orbital right there, you can easily do this. Okay, so keep that in mind for when you have problems on tests that you need to do quickly. Do it easy. Okay, so here's another problem. Let's cut this off, and we're gonna do a standard orbit. So the radius for standard satellite orbit is 400 kilometers. Above, this is very important, above the radius of the Earth. Okay, so you kind of have to add them together to get your total I'm not drawing a picture. I'm just going to go into the first question. What is the speed of the orbital? What is the speed of that orbital? And the nomenclature for that would just be v orbital. So we do the same old thing. G M E R square root v orbital. Okay. Turns out, of course, our orbital is equal to, and I really shouldn't call this R, I should call that an H. And our orbital is just RE plus HSS. So that's our orbital down here. 7,670 meters per second when you plug in the 5.96 times 10 to the 24 times 6.67 times 10 to the minus 11, and we're dividing by, I don't want to write all that out, so I'm going to write this, and then you take the square root. Okay, so that gives us that. Okay, B, what is the period? What is the period T? So we can quickly just come over and say T is equal to 2 pi r over v orbital. Again, we're multiplying 2 pi times the radius of the Earth plus the distance from the surface of the Earth that the orbital is. And we're going to divide by our 7670 meters per second. And so T ends up being 5.55 times 10 to the third meters per second. So that's our period. Okay. What is that? What's 5.55 times 10 to what does that mean to us? That means 1.54 hours. So if you notice, that's an hour and 32.5 minutes. 1 hour, 32.5 minutes. And that's right around 90 minutes. And that's perfect. I don't know if you guys have ever done... okay, so if you're camping in the wilderness, when I saw this, I was at Lake Powell. Back when Lake Powell had water. We were out on the boat. It's late at night. We're looking up at the stars, and it's so dark out there that you can actually see these blinking satellites go north to south. I'm going to do a blinking satellite going north to south. It would do that, and then about 90 minutes later, we'd see it happen again. And I started timing it. I was like, oh man, how often is this happening? And, you're on the houseboat, so of course you're drinking, and it's late at night. but it was 90-minute intervals roughly is what I had found. And that totally makes sense. And I didn't know that that's what I was measuring was a satellite. The ones that go north to south are often weather satellites and or spy satellites. Okay, you didn't hear that from me. Okay, so what if we circle the planet at the surface? Okay, so we're doing it right at the surface. Let's find out all these things for being right at the surface. So first of all, we want to know what V orb is. Okay, so V orb equals our mass of the Earth times gravity divided by the radius of the Earth. This is a pretty simple one. We don't have to add or subtract anything, so I'll actually do all the numbers for you. 10 to the 24 times 6.67 times 10 to the minus 11. And we're going to divide that out by 6.36 times 10 to the 6 meters. And we're going to take the square root. Awesome. V orb equals 79.06 meters per second. What was it at the regular, our V orb up here was 7,600, almost 7,700 meters per second. At Earth, at the surface of the Earth, we're doing 79.06. Not really that much faster. What was it at geosynchronous? 3,070. So we really dropped off our speed with relationship to the Earth. As we got closer to the surface of the planet, we sped up. Okay, what is that a statement of? Pretty much a statement of conservation of angular momentum. Okay, let's not beat that horse anymore. So let's do this. We want to find out what the period of rotation would be. So we're going to do our 2 pi times our radius of the Earth, and we're going to divide by V orb. So we've got 6.283 times the radius of the Earth, which is 5.96. It is 6.36 times 10 to the 6 in meters. And we're going to divide that by velocity of the orb, which is 79.06. And that's going to give us seconds. So RT in seconds. 5.05 times 10 to the 3 seconds. And all right, so that's meaningless to most people, but 1.4 hours, which is approximately 1 hour and 24 minutes, or a nice good long movie, 84 minutes. So it's still going around the Earth pretty fast, right? We're doing this pretty fast. 84 minutes. That doesn't take very long. So that's kind of neat, right? Okay, so what's our energy in a circular orbit? Oh, that's always fun. So let's look at our energy in a, and I'm saying that it's circular. We talked about it earlier, but I'm going to point it out again. Energy in a circular orbit. Okay, we're not dealing with ellipticals. So the first thing you got to do is do our free body diagram. Okay, and if we say that our positive is going away from the mass and negative is going in, our force of gravity is pointing down. Our centripetal acceleration would be pointing down. Not a force, so we're not applying it to our body of our test mass. That's our test mass. So let's do it. We've got the sum of the forces is equal to minus MAC, and that equals minus force of gravity and that equals minus mv squared over r. So this one is our force of gravity. This one is our centripetal force. And the same as this because that's our force net. And these two are the same. So we've got our equation technically right here. And we can start canceling stuff, right? We can cancel this, we can cancel that. We can cancel that one, and we can cancel that one, just like we did before. And we'll end up, if we want to, we can end up back with solving for v, but we don't want to do any of that. In fact, I'm mad at myself for doing that. I want to leave those things. So let's put the m back. Let's do this instead. We're going to solve mv squared equals mmg. And now I am canceling one of the r's because I'm putting the mv squared, I'm putting the r on this side on top of in the numerator on the other side, canceling out one of our r's. So we're left with just one r. The negative sign, of course, goes away. And this happens to equal 2 times our kinetic energy. That's why we wanted to do it this way. So that gives us that our kinetic energy is equal to 1/2 mv squared, which equals, we're just going to divide by 2, our mg over r. Okay. And of course, we know that our energy total, and I'm going to just say total as an energy because we're dropping friction, pretty much not even thinking about friction anymore in these orbits. So I'm just going to say that the energy is equal to our K plus our U. And they're all a function of r. So let's write them out. K is a function of r, and u is a function of r. And we had earlier seen, today in class actually, that our function of r is minus mg over r for our potential energy. Oh boy. They said the allergies were going to kick up today, and they did. Okay. So we know this, all right? So now we've got one of them. We know this one, so we've got the other. And we can then say that our E of R is equal to mmg over 2r minus mmg over r. Okay. I don't know if you guys have realized this, but we've got half here. We've got a whole here. If you have a whole minus a half, that leaves you with half. So ER is equal to a half, but it's the negative half. So mg over 2r. And that is our energy as a function of radius. So if you're in a certain radius and you don't have any excess energy, kinetic, you just have your potential energy being in that radius, this is your energy, okay? So it's negative because you're in a potential well. So let's look at what that means. So let's look at that equation. We're going to bring it all the way to this point. We're going to look at that equation. And we're going to look at it in a very nice graph here. Quality graphing skills. We have, not that. We have, this is what we'll call E equals 0. And then, of course, you can go up to infinity and beyond if you really choose to. Buzz Lightyear. All right. So in order to get to 0, you have to reach escape velocity. All right. What do we have here? We have this point is r equals 0. So technically, we'd have to eliminate this whole bit from our curve because you have to have mass of the actual object itself. So this is a no-go region, right? And then you actually have the radius of the planet itself. Okay, so here's, if we're going to say r goes out that direction and r goes out this direction, this is radius of the large mass object, okay? Okay, and then we're going to select this point as our maximum radius, and that equates to this point here. for this amount of energy. So this is the energy at R max. Okay? So all we get is this region to move around in. So all of this region from there to there, and I should erase this part. We get that to move around in freely. Really, that's kind of a misleading thing. Let's get rid of that. That's misleading. We have this region that we're okay traveling in, back and forth along this path. Okay? We can do things, but we have this much energy, and we're going to go back and forth along that path. We can go from the minimum to the maximum R, back and forth, and we're going to do it along this curve. Okay? That's our energy curve. Okay. What if we want to escape? We have to have enough energy to escape, which means we need to be in this region up here. And once we have that much energy, we can escape. Okay? That escapes the orbit. Anything bigger than this. So that is why this negative sign is here. So this is an important negative sign, because what we're saying is you're in a gravitational well. Okay? Your energy is less than 0. You're trapped by that object, which brings me back to the XKCD. Really, really, really look at that XKCD. Look at that comic strip. I don't know what else to call it. It's kind of a comic. It's not. I don't know. But at any rate, Randall Munroe does those, and he's brilliant. I really like his work. Okay, so this is the time when I tell you that I would recommend that you guys look at example 1312. I'm not going to do it. 13.12 in the book. Okay, so look at that in the book, and you'll want to look at that. All right, that's enough about that. Let's do a thing where we talk about inside masses and all of that jazz. Yeah, let's just go with okay. So we've got a couple of circles here, and if I could do a compass on a touch screen, that would be awesome. But pretend these are perfect circles, and there's only mass. We'll make it this color. There's only mass here. Okay, so this is where the mass is. This is where the mass is. We're still talking about gravity, but this time, this actually is more of a gravitational field question than anything else. Okay, and this is, you're going to do the same thing when you get to electromagnetics, so pay attention. Okay, so what do we have? We have a radius RA to the inside. Point A. Okay, and then we have another point B here. That's radius RB. And then we have another point outside, point C. So we've got the three places. I don't know if you want to take my word for this, but inside at point A, that's inside all of the masses, our gravitational potential let's do the force. Okay, the force of gravity as a function of R, that's going to be 0. So anything that is inside here, any of these points, have no forces pulling them any direction. Okay, because all the mass on the outside balances out in that inner circle. So we get 0. At point B, depending on the density of that material, well, we'll get to that in a second. Point B will actually have something that is not equal to 0, or I shouldn't say not equal, I should say greater than 0. Depends on which way you're going, I suppose. So that's that. And then at point C, of course, it'll be even more mass pulling you in. So that's even more than at point B. However, the inner ring, we'll call it ring 1 and ring 2. The inner ring is ring 1. That's the only mass that point B is attracted to. Okay? So the mass, not the little mass, the big mass. Mass is ring 1. And here, the mass is both ring 1 and 2. Here, mass equals 0. This is a Gauss's law thing. I don't know if you guys are going to appreciate that next semester, what I just said, but it's a Gauss's law thing. But let's do something more interesting. Instead of talking about zeros and stuff, let's actually look at this in a force way. So here's 0, and we're going to get to a certain point. Here's the thickness of ring 1. Here's the thickness of ring 2. And on the inside, our force is going to be nothing till we get to this point. As soon as we get to that point, we're going to start going up, right? And if the density We talked about this on the inside in one of my other the video lectures. Depending on the density of the material, so we can have density 1 and we can have density 2, which is greater than density 1. If it's density 1, we'll have this small little slope. If it's density 2, we'll have a larger slope, right? So your gravitation force will be larger if it's more dense, right? That makes sense. So we're going to go there. It's proportional to that, so I'm going to do a little proportional sign. It's not alpha, it's proportional. That's what the symbol for proportionality is. Then gradually, there's nothing anymore, so you're going to fall off as 1 over r squared. They're going to fall off like that. But then we're going to come back. We've got this same thing. And we've got density 1. And we've got density 2. And then those guys will again fall off as r squared. And that's pretty much what it looks like. These are our f of r's, depending on the density of the material. Okay, f of r and our test mass times g of r, which is mg over r squared. At this point, on the inside, it's linear. I'm not going to go back and show you that equation. That doesn't matter. So here we go. We're finally basically to the end of gravity. We've had some lovely videos. I said this in class, but I'll say it again because I think it's important. 13.6 is about tidal forces, and I really think that that's interesting. But you guys know my feeling on entropy and friction and all that. These are frictions that are developed from two massive planetary bodies that, because of them moving around each other, they actually squeeze and pull and tug on each other, forcing the planet to do, instead of a perfect circle, it gets oblong. And that obcentricity, I don't know if that's even a word, that eccentricity rotates. So the moon is rotating around us. That eccentricity rotates, and that's part of the what allows continental drift, helps the tectonic plates move. It helps a lot of stuff. It also helps surfers catch a wave. So that's an important one, I think. And then we've got 13.7. This one is definitely important, but it's just physics, right? It's just talking about physics, and I wrote it down earlier. Let's not use G. Let's do R mu nu. So R mu nu plus the gravitational constant, cosmological constant, I'm sorry, G mu nu equals 8 pi, and here's the universal gravitational constant popping in there, and then there's the speed of light quartered or quadrupled to the fourth. And then we've got T mu nu. Okay, this is a tensor, that's a tensor, that's a tensor, and that's a constant, cosmological constant. This is a constant, pi is a constant, that's a constant, and of course 8 is a constant. So it's a very interesting 13.7. If you're really into physics, this tells about gravity and how we think about it now. Okay, gravity in modern times. All right, so good. We've covered gravity. I think we're totally on track. We're going to do a test 4 review, and we'll take care of all that stuff on Tuesday. Thanks for watching.